All right.
So,
Brilliant. Thank you so much. I'll just say very quickly words. I don't want to take much time because we have two seminars today. So I don't know if you have to present all of the presentation. I don't know that. Maybe it's over. Yeah, that was, yeah. All right. Today, yeah. So very quickly, I don't want to take too much time. So today, this I see a few new faces. So this is the FCA, so Financial Computer Analytics seminar series. We are a group working on computational finance, and we kind of employ methods from statistics, statistical physics, statistical learning theory, mathematics, mathematical finance, and machine learning in problems in finance and economics, with a special kind of focus on complexity theory and methodologies and theories that are developed within the area of complex systems, so that are applied to computational science, but also economics, finance, and other systems. And so today we're going to present two seminars, which is kind of the first time for this seminar series, so that we had the opportunity to have two presentations, which will both be recorded and uploaded on our YouTube channel. So I don't want to take too much time. So roughly we'll start this one, and the next one will start in less than half an hour. So the first one is on double descent, benign over-parametrization, and it's an empirical study on double descent, and it will be presented by Yufei Gui, who is a student in a master in engineering of computer science, and supervised by actually Professor Matsuate, who's in the room. So thank you so much. I don't want to take more time. Your microphone is unmuted, right? Yes. I had to ask it. Yeah. Brilliant. So the recording is started. The floor is yours. Thank you so much.
hello everyone. So despite the introduction of the group properties and bringing something today that is not related to finance actually. So it's more of purely machine learning or from statistical learning perspective, and I'm only covering some of the very basic models of deep learning today. And okay, let's start it. So double descent. What is double descent? So we can look at these models here. So we have to start from a traditional statistical intuition that many of you might have heard of or studied when you are exposed to this field. It's called bias-variance trade-off, that when models are small, there will be high bias, and when the models are big, there will be high variance. We have to find the sweet spot between this bias and variance trade-off. However, in modern deep learning practices, we are sometimes using super big models that are highly parameterized and a super big number of samples. That sometimes opted or does not follow this traditional statistical intuition that we should use a profit model size that is sometimes small and that underparameterized. So this double descent curve here shows that the risk sometimes decreases while the capacity of model increases, which is experienced by many deep learning researchers and engineers nowadays, but not in the textbooks of traditional statistics. So this is a double descent phenomenon that the test loss of risk descends twice with respect to the increase in model capacity, or we will talk about model parameters. So, and here is some key definitions or phrases we will be hearing today. The first is equivalence threshold, which is usually defined as the minimum model capacity or number of parameters that is able to fully fit the training data, which means that is the smallest model size we can use to capture the data structure in our training set. It is previously recognized as when the number of parameters equals to the number of samples, but we will see that in more scenarios, they are not actually equal. And over-parameterization means that models that are bigger than the threshold. Sometimes it's super big, that's like 50 or even 500% times bigger than the interpolation threshold. Label noise we will encounter it in one of my studies. So it is defined as an external introduction of random noise by proportion P. And activation, layer-wise input-output vectors in a feed-forward process. So we will put the input layer, its activation is the data input. For the output layer, its output. For inner layers, we call it hidden features that are hidden activations that are not exposed to computations other than feed-forward and back propagation. Okay, so a quick, so I might be a bit quick today, so because I have a bunch of things to cover. Okay, so and some background knowledge, double descent. So despite I'm always introducing about parameters and model capacities, that's been studied from many different perspectives. From model-wise, which is what I'm focusing on, increasing model capacity. Sometimes it is called parameter-wise, when we consider it to increase model parameters. Sample-wise, which is increasing training samples, epoch-wise, increasing training epochs, that we are not covering today. And it also occurs on different models when it's on more traditional regression or random forest models, we call it linear double descent. And when it's on deep learning, we call it deep double descent. So which is what we are focusing on today. Okay, so here is some of the early studies, which is not very early, in 2019 and 2011, so 2021, that they found this double descent phenomenon in deep learning practices. Which the last paper is 2022 paper that extends study from empirical side also. And then, okay, this is the group research project I have been involved in during 2022 to 2023 that we tried to reproduce some of these early empirical samples and experiments of double descent. However, this experiment or this research project actually shows that the proposed double descent phenomenon is not universal in all deep learning practices. We will see that, for example, in the top left column, there's no double descent phenomenon occurring. And we actually find out that this phenomenon in the original paper is induced by a little bit biased experiment setup that is hard to reproduce to some extent. So this is the research project. I'm going and through it. Okay, so after we find that double descent is not that universal, it doesn't always occur. So we try to understand when will it occur and what factor does it relate to. And so we find this label noise. This is an experiment completed by Nigerian in 2021. That is here may not be very clear. Anyway, the upper lines refers to the increase in label noise, which I said before is random label or proportion introduced externally on CSS cipher. So we will see that this double descent phenomenon is enhanced with the increased label noise. When there's no label noise, there is the double descent phenomenon is hard to observe, but with its increase, it is much more robust and significant. As I said, it appears more in complex scenarios and with explicit label noise. So this leads to my this paper. I led this research and it is just accepted to actually 4. So here is some of the hypotheses and contributions that I have done. So deep learning models learn to separate the noise from the information in the training set through interpolating correct samples around noise samples to learn feature space. And prediction accuracy shares a similar tendency in the model's tendency performance with extension in model-wise. It might be a little bit of difficult to understand here, so I will be a bit into details here. So the hypothesis is when I observed with an increase in label noise, the generalization is enhanced in over-parameterized models compared to under-parameterized models. So here is a bit of hypothesis I have made. So first, an optimal classifier should yield accurate predictions for on-scene images, even if it was trained on similar images with an adversarial label. And considering the effect with the double decision phenomenon on over-parameterized models, large ones, we assume that large models test images akin to training images with labels are more likely to correctly classify by over-parameterized models. So until now, it is more rational, but my hypothesis is the closest labels with label training images could be correctly classified in the training process by over-parameterized models compared to the under-parameterized ones. And I use a KN algorithm in the training data set to reflect this interpolation strategy with the cyan line of the prediction accuracy here showed on this graph. So we can see that this is on CNNs on Cypher, this is C, I've also done the experiments on residual light neural networks. We can see that this prediction accuracy shares the same tendency with the generalization performance, and thus we can conclude there is somehow a statistical relationship between them, although it's not very casual or strong. It's not a strong argument, but it appears that this statistical relationship occur in different models and on different datasets. So this is the main content of this paper, and you will easily see there are certain regulations here. So like in empirical study cases, it's only on classification tasks. I'm planning to do it on NLP tasks also in the future. And the relationship is only statistical, not causal, like in theoretical studies, like in mechanism explanations. So, okay, and finally, I'm going to introduce some of the double descent research works from different perspectives and some works I'm still doing now. So here is three perspectives, three papers done by other researchers in recent years that focus on different perspectives. Geometric, which is a very interesting one, that it compares the expansion in model rest and the expansion in dimension of hidden feature spaces, which we call the hidden activation vectors. He compared this to expansion of high dimensional hyperspheres. I don't know if anyone has heard of this paradox of high dimensional hyperspheres, that with an increase in dimension, the unit hyperspheres volume and surfaces area actually decreases with respect to increasing dimension. Thus, he provides an interesting hypothesis that the increase in dimension of neural networks also leads to a decrease in this volume and surface areas, which is considered as a distribution of weight. And when we talk about shrink in distribution of weight, we consider it as an implicit regularization methodologies. Although, or we will say mechanism here because we didn't introduce this externally. So he made this interesting hypothesis concluded in this paper. However, he didn't give a very strong proof of it. Okay, the second one, smooth interpolation. So he calculated the sublet of loss landscape, which is somehow similar to my studies, but from a little bit different perspective. And he also proves that this sublet of loss landscape did affected by the over-parameterization models and the generalization performance. And finally, the sparsity in hidden linear activations, which we will see here. So first, we should know that no explicit regularization method, including a dropout, is applied, so that we can see that in the left figure, the super small or extremely small weights are very minimal in the network. That they are not penalized to zero. Most weights are still positive or negative, and they are active in the network. And however, but we can see from this figure by this figure that with the expansion in layer west, the effective activity ratio of neurons actually decreases from about 80% to 50% as an average. So this activity sparsity is a research focus of my current studies that I'm doing right now. So activity sparsity in over-parameterized models that promote generalization. So here's a simple fully connected networks of a small dimension of hidden features and a large dimension of hidden features. So I don't have much time, so I will jump quickly through some things. So here is a list of hypotheses I have raised and I am examining right now. So first, high-dimensional over-parameterized neural networks induce sparsity, which promotes generalization. So we have seen that there is some activation sparsity, at least in fully connected neural networks. And we also see that there is improved generalization performance in over-parameterized models. So this is a hypothesis that we can make that over-parameterization induces sparsity and promotes generalization. And the second hypothesis here is stating that in a classification neural network, the class function that we will talk about later, they actually detach with respect to increasing model mass and capacities. This is a little bit brave hypothesis I have made here. So go back to this picture. We can assume that they are all 5-class classification neural networks from the output layer. We can assume that in the first neural network, all neurons are deciders of all classes. They are always activated. There's no activated sparsity. So the class function of each class is the whole network. They are always active. However, in this data one is a stripe neural network with an expansion of model-wise or hidden layer dimensions. There are increased activation sparsity, and not all neurons are activated for each class. And there exists some class patterns or class functions that are subset of this neural network, but not the full neural network. So, for example, like for this class, only the below 3 neurons are activated, and the others are always activated. So some of the connections are not activated for this class, and in this perspective, I call that the class functions actually detached. So this is a hypothesis made, and below I will introduce 2 experiments that I'm trying to prove this hypothesis. First, a complexity of class functions. I believe you have somehow heard of red matter complexities. That the equation is the variable takes on -1 or 1 with equal probability to represent label noise, and the complexity of a given hypothesis space is measured by how well it can fit this random noise. And because due to computation ability limit, I cannot compute the red matter complexity of the whole training set. It is too complex. So instead, the hypothesis space is embedded only the hidden data space. And instead of measuring full data set, I measure subset of equal sizes that takes on this random little noise defined by red matter complexity, and use this as an estimate of the complexity of these class functions. And in this picture, we can see that the complexity of class functions somehow increases before the interpolation threshold. It's not very obvious, but yes, it is the peak occurs at around the interpolation threshold, and it decreases after that. Although may not be super uh, super clear with I didn't do it on very fast examples and average, but we can still see the pattern here is that the complexity of functions with respect to model capacity does not follow a monotonic trend. Instead, somehow like double descent, it increases before interpolation threshold and it decreases after. Such that we can see that the class functions complexity somehow decreases. And this can be used as a side proof of my previous hypothesis. And the second one is I measure the class-wise activation patterns. So here is the definition of it. It is basically a time-wise multiplication between two closed layer activations. So for example, if we are having a 3-layer neural network here, we have input, hidden, and output 3 layers. We measure the input and hidden layer activation matrix by doing a element-wise multiplication of the activation of input layer, which is the input, and the activation of the hidden layer, which is the hidden features. So that and we take average. Yes. Okay. We take average of these activation patterns to a class-wise basis to reflect a pattern of inner layer activations of each class. And we compare these class-wise activation matrices to reflect if this class function of neural networks really detects the over-parametrized neural networks compared to smaller ones. And here's a heat map. It's not very obvious, I understand. So of the similarities between class-wide activation matrices, it's on a class-wise basis, one-to-one, and the above line is about equal to the hidden layer, and the latter one is hidden to output layer. It's not very easy to understand, so we will go along with this one. The first is concatenarity, the second is Pearson correlation coefficient. We can see that first we look at the orange and blue lines. The orange is the input layer to hidden layer, the blue is hidden layer to output layer. And we can see that a little bit surprisingly, between input layer and the hidden layer, where sometimes we call it a representation layer, we get the representation from the input. The class-wise activation matrix, or we say activation patterns, does not differ much with respect to model capacities. However, for the hidden layer and upper layer, the activation matrices or activation patterns decreases monotonically with respect to increasing model capacity. So this is a little bit surprising that tells that this sparsity actually occurred in the hidden layer to upper layer, but not in the input to hidden layer. A little bit weird stuff is that I also measured the right line as the hidden features vectors to see if there's a pattern relation. And there's an increase in correlation coefficient compared to cosine similarity. So my current guess is that if you respect the magnitude, but I'm not super clear now. This is okay. So anyway, in the end, some of the unanswered questions include what is the mechanism between this induced activity sparsity? Is it due to a property of SVs I use, or is it a property of high-dimensional geometric or statistics? And the final question is, we have six sparsities in different places in a neural network, but does it really propose generalization? Does it have a connection to the generalized performance we have seen? That is it an implicit regularization? And I'm trying to design regularization methodologies to prove that. As I said, so it's to be continued. Okay, thank you. And any questions? I guess I have a few minutes for questions. So anyone has
So I'm not sure where we there's analysis of sparsity. These food sprouts support or even when the ground truth is sparse, doing basis descents, not so they have the sparse wave functions that so I'm not sure if there's a relation with everything sparse and increases generalization, there's still sparse.
Yes, I understand. So there are many different proposals, and even some proposals are equipped with theoretical or empirical selected derivations or empirical observations. So what I can say is so first it is some of the very simple machine learning techniques and tasks. I am trying to see if there is some activation sparsity here, and I'm also trying to understand if it's related to generalization, because some people have proposed this argument, but it has been less studied. I've definitely seen that sometimes sparsity is worsening the generative performance or worsening the model's abilities to learn or represent data. I will only say that also, as I said, because I'm doing it most from an empirical perspective, with sort of very strong theoretical support. Many of the conclusions here is not that strong actually. So thank you for your suggestion or from a different perspective. I think I will look into it because many of these studies are unconclusive right now. So thank you for your advice.
Thank you again. Thank you.